Okay, so this is section 3.2, synthetic division. And in Algebra 2, you spend a lot of time doing long division with polynomials. And we don't want to do this method in this course because it takes too long and it's very tedious, and it's not really a good method for what we need synthetic division for. So instead, we will generalize synthetic division as something like this. Take some polynomial and divide it by a factor that's, say, x minus c. So it has to be a linear factor in the denominator. And so c in this case would be 2 because this is x minus c. And the process is that you put c in a box, and then you write your coefficients of your numerator in descending order of their powers on each term. So this is to the squared, to the first, and then your constant. So you write the coefficients 1, negative 2 in a row. And then the process goes like this. You bring the first number down, then you multiply these two numbers, put it here, then add, then multiply 1 times 2, then put that number here, and then add. So the two numbers that are left to the left of your remainder are the coefficients of your quotient. So if we started with a squared term, then this is going to be x to the first. So this is 1x to the first plus 1 with a remainder of 0. And this remainder of 0 is very important. What that means is that x squared minus x minus 2 can be factored into, which you should know, x minus 2, x plus 1. And if I cancel out the x minus 2's, I'm left with x plus 1, which is what I happen to get for my remainder. Now, we're not always that lucky. Polynomials are not always divisible. So in order to see what happens when we don't get a remainder of 0, let's check out this example where we have a 4th degree. So what would c be in this case? In this case, c would be negative 1 because remember we can rewrite in the bottom as x minus c. So this is x minus negative 1. So we line everything up. Notice that I have a 0 here. I needed a placeholder because this is x to the 4th, and then I jump to x squared, so I don't have an x cubed term. So I have to go 0x cubed minus 1x squared plus 3x minus 2. Bring down the 3, then we multiply, put it here, add, multiply, add, multiply, add, multiply, add. And we're not so lucky to get a remainder of 0 here. So how do we write this? Well, this started with a 4th, and I took 1 out, so that takes me down to a cubed. So I will put this as the leading coefficient, and this will be x to the cubed. So for my final answer, we'll write it like this, that the division that we just did, which is this is what we were asked to do, is equal to the quotient of what we got, so 3x cubed minus 3x squared plus 2x plus 1, plus this is my leftovers, this is my remainder, negative 3 over x plus 1. This is how you would write the remainder in this case. There's an alternative way to write this, and it may be more intuitive to some of us that are used to multiplying polynomials and things like that. If you think about multiplying this entire thing by x plus 1, if I distributed this x plus 1 to here, it would cancel. If I distributed this x plus 1 to here, I would just get the product of this times x plus 1. And then lastly, I would multiply this by the remainder, and the x plus 1's would cancel. So what we would end up with is something like this. That this polynomial, this polynomial we had in the numerator, is equal to the product of these two polynomials, and will be so close to this that we'll just need to subtract 3. And the best way to think about this is with actual numbers. Think about just dividing 27 by 5, for example. How close can we get? Well, the answer would be 5 plus a remainder of 2/5. 5 plus 2/5 is 27/5. But you could also think about that if you multiply both sides by 5, I get 27 equals 25 plus 2, which is a true statement. So we can decompose polynomials much like we decompose numbers. It's very similar. And if this term is a factor of the numerator, then we wouldn't have a remainder. And it would just be a fact that this would be factored into the quotient times the function in the bottom.